From the coldest and most silent place on Earth, Antarctica, scientists detected something they should never have heard: a strange radio signal rising through the ice, a signal that defies the laws of physics. Before we unravel this mystery, I want to ask you, where in the world are you watching from, and what time is it right now? It's always incredible to see a map of curious minds gathered here from every corner of the Earth. If you find these journeys into the unknown fascinating, subscribing ensures you'll never miss the next exploration into science's greatest mysteries. Now, let us return to Antarctica, to the frozen frontier where this impossible signal was first heard. Beneath the icy silence of Antarctica, a place so remote it feels alien even on our own planet, something impossible was heard. Not the howl of wind over frozen cliffs, not the groan of shifting glaciers, but a signal, a radio wave unlike anything ever detected before. It didn't come from a satellite, it didn't come from space debris, it didn't come from human hands. It came from below, rising up through the solid ice of Antarctica, piercing detectors built to study the most elusive particles in the cosmos. Scientists had designed the ANITA experiment, the Antarctic Impulsive Transient Antenna, to listen for high-energy neutrinos, ghostly particles that pass through matter as if it doesn't exist. But instead of catching neutrinos falling from the sky, ANITA heard something else: particles moving the wrong way, from the ground up, as if reality itself had been flipped upside down. This wasn't supposed to happen. According to the laws of physics, according to the standard model that governs particle interactions, signals like this are impossible. For years, data piled up, each anomaly adding to the mystery. Was this a glitch? A misunderstanding? Or was Antarctica whispering a secret about the universe that could rewrite everything we know? If the signals are real, they suggest the existence of new physics, particles that shouldn't exist, forces we don't yet understand, perhaps even a mirror universe running alongside our own. A radio signal from Antarctica may sound small, but its implications are vast. They could challenge the foundation of physics, hint at hidden dimensions, or reveal that reality is stranger than our equations can contain. This is the story of the strange radio signal that came from Antarctica, and the decade-long mystery that continues to baffle the world's leading physicists. Scientists had designed the ANITA experiment, the Antarctic Impulsive Transient Antenna, to listen for high-energy neutrinos, ghostly particles that pass through matter as if it doesn't exist. But instead of catching neutrinos falling from the sky, ANITA heard something else: particles moving the wrong way, from the ground up, as if reality itself had been flipped upside down. This wasn't supposed to happen. According to the laws of physics, according to the standard model that governs particle interactions, signals like this are impossible. For years, data piled up, each anomaly adding to the mystery. Was this a glitch? A misunderstanding? Or was Antarctica whispering a secret about the universe that could rewrite everything we know? If the signals are real, they suggest the existence of new physics, particles that shouldn't exist, forces we don't yet understand, perhaps even a mirror universe running alongside our own. A radio signal from Antarctica may sound small, but its implications are vast. They could challenge the foundation of physics, hint at hidden dimensions, or reveal that reality is stranger than our equations can contain. This is the story of the strange radio signal that came from Antarctica, and the decade-long mystery that continues to baffle the world's leading physicists. Heses suggests that our cosmos might be paired with an anti-universe where time runs backward, antimatter dominates over matter, and physical processes unfold in reverse. Antarctica is unlike any other place on Earth. Vast, desolate, and unforgiving, it holds over 90% of the world's ice in sheets that stretch up to 4.8 kilometers thick. Temperatures plunge below 80 degrees Celsius. Winds sweep across the plains like invisible knives, reaching speeds that would tear apart most human structures. It is, in many ways, the closest thing we have to an alien world without leaving Earth. For scientists, this harshness is not a barrier. It is an opportunity. Antarctica's frozen landscape is the perfect backdrop for studying cosmic mysteries. Its thick ice sheets act like transparent glass to particles from the universe, while simultaneously serving as a natural particle detector when cosmic rays interact with the frozen water molecules. The continent's radio silence, free from the electromagnetic interference that plagues populated areas, creates a natural laboratory unmatched anywhere else on the planet. The ice itself becomes part of the experiment. When high-energy particles strike the Antarctic ice, they create cascades of secondary particles that emit brief but detectable radio pulses, a phenomenon known as the Ascarian effect. These radio signals can travel through ice with minimal absorption, making them ideal messengers from the cosmic depths. Enter ANITA, the Antarctic Impulsive Transient Antenna. This is no ordinary scientific instrument, but a testament to human ingenuity in the face of extreme conditions. Picture a massive balloon, 37 kilometers above the ice, carrying a sophisticated array of radio antennas that scan the frozen wasteland below. The balloon itself is a marvel of engineering, designed to withstand the fierce Antarctic winds while maintaining precise positioning for weeks at a time. ANITA's mission was elegant in its simplicity. Listen for faint radio pulses caused when high-energy neutrinos collide with ATO, misses deep within the ice. Neutrinos are among the strangest known particles, nearly massless, electrically neutral, and capable of passing through entire planets undisturbed. They are the universe's ultimate messengers, carrying information from the most violent cosmic events, supernovae explosions, colliding black holes, and the cores of distant galaxies where matter spirals into oblivion at near-light speeds. By studying these elusive visitors, scientists hope to probe the universe's most violent events in ways that traditional telescopes could never achieve. Unlike light, which can be absorbed or scattered by dust and gas across cosmic distances, neutrinos travel in straight lines from their sources, arriving on Earth with their original stories intact. The experimental setup was ingenious. ANITA would circle Antarctica at stratospheric altitude, its antennas pointed downward toward the ice. When an ultra-high-energy neutrino struck the ice below, it would create a brief shower of particles, which in turn would emit a characteristic radio pulse. By detecting these pulses and analyzing their properties, their strength, frequency, and direction, scientists could reconstruct the original neutrino's energy and trajectory, potentially tracing it back to its cosmic birthplace. But what ANITA found was not what anyone expected. Starting with its first flight in 2006 and continuing through subsequent missions in 2008, 2014, and 2016, the detector began picking up signals that defied explanation. Instead of neutrinos plunging downward into the ice as expected, ANITA caught signals that seemed to rise up from below the horizon. These weren't faint, questionable blips in the data. They were strong, clear, and repeatable. The problem was fundamental. According to our understanding of physics, this should be impossible. Ultra-high-energy neutrinos cannot travel through the Earth. At the energies ANITA was detecting, neutrinos would interact with the dense rock and metal of our planet's interior long before they could emerge on the opposite side. The probability of them making it through was less than 1 in a million. Yet there they were, signals appearing to come from deep within the Earth, emerging at steep angles through the Antarctic ice, as clear and strong as if they had traveled through empty space. The implications sent shockwaves through the physics community. The ice of Antarctica had become more than just a stage for cosmic particle detection. It had become the site of a puzzle that challenged the very foundations of our understanding of reality. The signals suggested that either our knowledge of particle physics was incomplete or something far stranger was happening beneath the frozen continent. As data accumulated from multiple ANITA flights, the mystery only deepened. Each new detection added another piece to a puzzle that seemed to grow more complex rather than clearer. Scientists found themselves facing a choice. Either accept that their instruments were systematically malfunctioning in identical ways across multiple missions, or consider the possibility that Antarctica was revealing something fundamentally new about the nature of reality itself. The stage was set for one of the most intriguing scientific mysteries of the 21st century, a mystery that would challenge Nobel Prize-winning theories, inspire wild speculation about parallel universes, and ultimately force physicists to question whether they truly understood the cosmos as well as they thought they did. The first hints of something unusual appeared in the data from Anita's inaugural flight in December 2006. Buried deep within terabytes of recorded radio signals were a few pulses that didn't match any known pattern. At first, the research team led by Peter Gorham at the University of Hawaii dismissed them as instrumental noise, the kind of electronic hiccups that plague sensitive equipment operating in the harsh Antarctic environment. But as subsequent flights took to the skies above Antarctica, more strange signals appeared. The 2008 Anita 2 mission detected similar anomalies. Then came Anita 3 in 2014 and Anita 4 in 2016. With each mission, the pattern became clearer and more troubling. Anita was consistently detecting radio pulses that seemed to originate from beneath the Antarctic ice sheet, traveling upward at impossible angles. The most famous of these anomalous events occurred during the Anita Y and Anita 3 flights. Two particularly strong signals stood out from the background noise like flares in the darkness. Both showed characteristics that appeared to match tau-neutrino interactions, but with one crucial, impossible difference. They were coming from the wrong direction entirely. To understand why this was so shocking, imagine throwing a baseball at a concrete wall and having it emerge from the other side with more energy than when it went in. That's essentially what Anita was observing with these upward-traveling particles. When ultra-high-energy neutrinos interact with matter, they typically create tau leptons, unstable particles that quickly decay, producing the radio signals Anita was designed to detect. Under normal circumstances, these interactions should occur in the ice directly below the detector, with the resulting radio waves traveling upward to the balloon. What Anita was seeing, however, suggested that neutrinos had somehow traveled through the entire Earth, from the opposite side of the planet, maintaining their high energy despite passing through thousands of kilometers of rock, magma, and metal. The physics simply didn't add up. At the energies in question, ranging from 0.6 to 2.8 eeV exaelectron volts, energies so high they dwarf anything produced by human-made particle accelerators, neutrinos should interact strongly with matter. The Earth's cross-section for these particles should be enormous, meaning they would almost certainly be absorbed or deflected long before reaching Antarctica. Dr. Stephanie Wissel, now an associate professor at Penn State who worked on the Anita team, described the problem succinctly. The radio waves that we detected were at really steep angles, like 30 degrees below the surface of the ice. By our calculations, the anomalous signal had to pass through and interact with thousands of kilometers of rock before reaching the detector, which should have left the radio signal undetectable because it would have been absorbed into the rock. The initial scientific response was skeptical, as it should be. Extraordinary claims require extraordinary evidence, and the physics community began scrutinizing every aspect of the Anita experiment. Could the signals be instrumental artifacts? Reflections from atmospheric layers? Contamination from human-made radio sources? One by one, these conventional explanations were ruled out. The signals showed the characteristic frequency spectrum and polarization patterns expected from tau-neutrino interactions. Their timing and directional information were consistent across multiple independent detector channels. Most importantly, they occurred during periods when Anita was flying over the most remote regions of Antarctica, far from any possible human interference. The research team performed extensive Monte Carlo simulations, running millions of virtual experiments to determine how often such signals might appear by chance. The results were sobering. the probability of seeing even one such event by random fluctuation was less than 1 in 1,000. Seeing two similar events suggested odds of less than 1 in a million. As word of the anomaly spread through the particle physics community, theories began to emerge. Some suggested the signals might represent a new type of neutrino interaction, previously unknown to science. Others proposed that the particles might not be neutrinos at all, but some exotic form of matter that could pass through the Earth more easily than anything in the standard model. The most radical theories went even further. Could these signals be evidence of sterile neutrinos, hypothetical particles that interact only through gravity and the weak nuclear force? Or might they represent something even stranger, particles from a parallel universe leaking into our reality through quantum mechanical processes we don't yet understand? Each possibility was more extraordinary than the last, but the data remained stubbornly consistent. Independent analysis by multiple research groups confirmed the basic observations. Anita had detected real signals coming from below the ice at energies and angles that challenged our understanding of physics. The mystery was no longer whether the signs existed. They clearly did. The question had become far more profound. What could possibly create such signals, and what did their existence mean for our understanding of the universe? As recent studies published in Physical Review Letters in 2025 continued to analyze the anomaly, the implications grew ever more intriguing. The signals refused to fit into any conventional category, standing as a monument to the limits of human knowledge and a tantalizing hint that reality might be far stranger than anyone had imagined. The standard model of particle physics stands as one of humanity's greatest intellectual achievements. Developed over decades of painstaking research and confirmed by thousands of experiments, it describes the fundamental particles that make up reality and the forces that govern their interactions. From the electron to the Higgs boson, from electromagnetic radiation to the strong nuclear force, the Standard Model has predicted phenomena with breathtaking accuracy, sometimes to more than 10 decimal places. This theoretical framework has guided our understanding of everything from the fusion reactions that power the sun to the quantum fluctuations that may have seeded galaxies in the early universe. It has enabled technologies from medical imaging to particle accelerators, and it earned its creators multiple Nobel Prizes. By the early 21st century, the Standard Model seemed nearly complete, a mature theory with only a few loose ends remaining to be tied up. Then Anita detected its impossible signals. The problem runs deeper than a simple contradiction between theory and observation. The Anita anomaly strikes at the heart of how neutrinos interact with matter, one of the most precisely understood aspects of the Standard Model. At low energies, neutrinos barely interact with anything. They can pass through light years of lead without being absorbed. But as their energy increases, so does their likelihood of interacting with matter. This relationship is precisely quantified by what physicists call the neutrino-nucleon cross-section. For the ultra-high energy neutrinos that Anita detected, this cross-section becomes enormous. A neutrino with an energy of 10^18 electron volts, (1 eeV), has roughly the same chance of interacting with a proton as a marble has of hitting the ground when dropped from shoulder height. When scaled up to the billions of protons in every cubic centimeter of rock, the Earth becomes essentially opaque to such particles. Yet Anita's signals suggested that these high-energy neutrinos had somehow traversed the entire planet, traveling through approximately 12,800 kilometers of increasingly dense matter, from the thin crust through the rocky mantle and into the iron-nickel core, then back out again, without being absorbed or significantly deflected. If we trust the Standard Model's predictions, the probability of this happening even once should be less than 10^7, 1 in 10 million. For it to happen twice, as Anita observed, the odds become vanishingly small. It would be like flipping a coin and getting heads 1,000,000 times in a row. This contradiction has forced physicists to consider three possibilities, each with profound implications. First, the Standard Model is incomplete. Perhaps neutrinos interact with matter differently at ultra-high energies than theory predicts. Maybe new physics emerges at energy scales that our particle accelerators cannot reach. This wouldn't necessarily invalidate everything we know, but it would require significant modifications to our understanding of fundamental interactions. Second, the particles Anita detected aren't neutrinos at all. This opens even more radical possibilities. They might be sterile neutrinos, hypothetical particles that interact only through gravity and the weak nuclear force, making them far more penetrating than ordinary matter. Or they might be something even more exotic, supersymmetric particles, axions, or other theoretical entities that exist beyond the Standard Model. Third, and most speculatively, the signals might represent evidence of physics so new that we don't yet have names for it. Some theories suggest that the Anita events could be signatures of extra dimensions, quantum tunneling on cosmic scales, or even interactions with a parallel universe where the laws of physics run in reverse. The scientific establishment has responded to these challenges with characteristic rigor. Independent experiments have been designed to test the Anita observations. The IceCube Neutrino Observatory, buried deep in the Antarctic ice, has searched for similar upward-going events. The Pierre Auger Observatory in Argentina has scanned its massive dataset for corroborating signals. So far, these searches have come up empty. Recent analysis published in 2025 by teams including Penn State researchers found no evidence of similar anomalous events in 15 years of data from the Pierre Auger Observatory. This null result doesn't disprove the Anita observations, but it does constrain the possible explanations. Dr. Wissel notes that this lack of corroboration actually deepens the mystery. While the origin of these events is still unclear, our new study indicates that such events have not been seen by an experiment with a long exposure like the Pierre Auger Observatory. So it does not indicate that there is new physics, but rather more information to add to the story. The implications extend far beyond neutrino physics. If the Standard Model is wrong about something as fundamental as how particles interact with matter, what else might we have misunderstood? Could there be entire classes of phenomena invisible to our current theoretical framework? The Anita anomaly has become a crack in the foundation of physics. Small, perhaps, but potentially capable of bringing down the entire edifice of our understanding. As physicists continue to grapple with these questions, one thing has become clear. The universe is under no obligation to conform to human expectations. Reality, it seems, may be far stranger and more complex than even our most sophisticated theories can describe. Science thrives on skepticism. Every extraordinary claim must run a gauntlet of scrutiny, alternative explanations, and attempts at replication before it can be accepted as genuine. The Anita anomaly has faced this process with particular intensity, as physicists worldwide have searched for conventional explanations that could account for the seemingly impossible signals without requiring new physics. The first line of defense against extraordinary claims is always instrumental error. Could Anita's complex electronics, operating in the harsh Antarctic environment, have malfunctioned in a way that created false signals? The research teams have spent years examining this possibility, conducting extensive calibration tests and cross-checking data from multiple independent detector channels. The balloon-borne experiment faces unique challenges that ground-based detectors avoid. Temperature fluctuations as extreme as 60 degrees Celsius between day and night can affect electronic components in unpredictable ways. Cosmic ray impacts on the sensitive electronics could create spurious signals. Even the motion of the balloon itself, spinning slowly as it circles Antarctica, might introduce systematic effects that could be mistaken for particle detections. Yet detailed analysis has failed to identify any instrumental cause for the anomalous signals. The events show characteristic features. specific frequency patterns, polarization signatures, and timing correlations across multiple antennas that would be extremely difficult to produce artificially. Moreover, the fact that similar anomalies appeared across multiple ANITA flights with different instrumental configurations makes systematic error increasingly unlikely. A more intriguing possibility involves atmospheric and ice-related effects that might bend or reflect radio waves in unexpected ways. Antarctica's unique environment creates complex layering in both the atmosphere and the ice sheet that could potentially redirect signals from conventional cosmic ray interactions. Dr. Wissel acknowledges this possibility. My guess is that some interesting radio propagation effect occurs near ice and also near the horizon that I don't fully understand, but we certainly explored several of those, and we haven't been able to find any of those yet either. The research teams have investigated whether temperature inversions in the Antarctic atmosphere could create radio mirages that bend signals from distant sources, making them appear to come from below the horizon. They've studied whether the boundary between the ice sheet and bedrock could act as a reflecting surface, bouncing signals in ways that confuse the directional reconstruction. Sophisticated computer simulations have modeled radio wave propagation through the complex, layered structure of Antarctic ice. These studies have examined how factors like varying ice density, trapped air bubbles, and the presence of liquid water at the base of the ice sheet might affect signal paths. So far, no combination of known atmospheric or glaciological effects can fully account for the observed anomalies. Another conventional explanation focuses on the possibility that the signals represent misidentified cosmic ray events. Ordinary cosmic rays, high-energy protons, and atomic nuclei from space constantly bombard Earth's atmosphere, creating extensive air showers of secondary particles. Under certain geometric conditions, these showers might produce radio signals that could be confused with upward-going neutrino events. This explanation has been studied exhaustively through Monte Carlo simulations that model millions of cosmic ray interactions. While such events can occasionally produce confusing signals, their expected rate is far too low to account for the ANITA observations. Moreover, cosmic ray events would produce different frequency spectra and polarization patterns than what ANITA detected. The most rigorous test of the ANITA anomaly has come from independent experiments designed to detect similar phenomena. The IceCube Neutrino Observatory, with its cubic kilometer of instrumented ice deep beneath the South Pole, should be ideally positioned to observe upward-going ultra-high-energy neutrinos if they exist. IceCube's analysis of its data has been sobering for those hoping to confirm the ANITA observations. Despite years of operation and sensitivity to the same types of neutrino interactions that ANITA claims to have detected, IceCube has seen no clear evidence of similar anomalous events. This null result places significant constraints on any exotic physics explanations for the ANITA signals. Similarly, the Pierre Auger Observatory in Argentina, the world's largest cosmic ray detector, has found no evidence of anomalous upward-going events in its 15-year dataset. If the ANITA signals represented a general phenomenon of ultra-high-energy particles traversing the Earth, Auger should have detected them. These non-detections by independent experiments have led some physicists to suggest that the ANITA anomaly might be unique to the specific experimental configuration and Antarctic environment. Perhaps the signals result from an unusual combination of factors: ice properties, atmospheric conditions, and instrumental sensitivity that exists nowhere else on Earth. This possibility highlights one of the challenges in interpreting the ANITA results. Unlike laboratory experiments that can be repeated under controlled conditions, balloon-borne detectors over Antarctica operate in a constantly changing environment. Factors like ice surface conditions, atmospheric pressure, and even the Earth's magnetic field vary with location and time, making exact replication extremely difficult. Despite these challenges and the lack of independent confirmation, the ANI-TA anomaly has proven remarkably persistent. Each attempt to explain it conventionally has failed to fully account for the observed signals. The events remain genuinely anomalous, unexplained by known physics and unconfirmed by other experiments. This persistence has gradually shifted the scientific discussion from whether the signals are real to what they might represent. Even skeptics acknowledge that ANITA has detected something unusual, even if they disagree about its interpretation. The mystery has evolved from a potential experimental error into a genuine scientific puzzle that continues to challenge our understanding of particle physics and the cosmos. When conventional explanations fail and the evidence refuses to disappear, science must venture into uncharted territory. The persistent nature of the ANITA anomaly has forced physicists to seriously consider possibilities that once seemed like pure speculation: new particles, hidden dimensions, and physics beyond the standard model that might finally explain why these impossible signals continue to emerge from the Antarctic ice. The most scientifically conservative explanation for the ANITA anomaly involves sterile neutrinos, hypothetical particles that have been theoretical curiosities for decades but never definitively observed. Unlike the three known types of neutrinos, electron, muon, and tau neutrinos, sterile neutrinos would interact only through gravity and possibly the weak nuclear force, making them far more elusive than their ordinary cousins. The appeal of sterile neutrinos as an explanation for ANITA's observations lies in their unique properties. Because they interact so weakly with matter, ultra-high-energy sterile neutrinos could potentially traverse the entire Earth without being absorbed, unlike ordinary neutrinos that would be stopped by the planet's dense interior. Upon reaching the Antarctic ice, these sterile neutrinos might transform into ordinary tau neutrinos through a process called neutrino oscillation, suddenly becoming detectable just as they emerge from below. Research published in Physical Review in 2018 explored this possibility in detail, showing that sterile neutrinos with specific mass and mixing properties could indeed produce signals similar to those observed by ANITA. The calculations suggested that if such particles exist, they might explain not only the Antarctic anomaly, but also certain puzzling observations from other neutrino experiments around the world. However, the sterile neutrino explanation faces significant challenges. The IceCube Neutrino Observatory has conducted extensive searches for these elusive particles and found no evidence for their existence, at least in the energy ranges and mixing scenarios that would be required to explain ANITA's observations. This absence of corroborating evidence has led many physicists to look for more exotic explanations. Supersymmetry, one of the most beautiful theoretical frameworks in modern physics, predicts that every known particle has a heavier superpartner waiting to be discovered. This elegant theory could explain several mysteries of modern physics, including the nature of dark matter and the hierarchy problem that plagues our understanding of particle masses. Could the ANITA signals represent evidence of supersymmetric particles? Some theoretical models suggest that ultra-high-energy cosmic rays could produce cascade showers of supersymmetric particles when they interact with Earth's atmosphere. These exotic particles might have penetrating properties that allow them to travel through the planet more easily than ordinary matter, potentially explaining the upward-going signals that ANITA detected. The supersymmetric explanation is particularly intriguing because it could connect the ANITA anomaly to some of the deepest unsolved problems in physics. If confirmed, it would represent the first evidence for supersymmetry at energy scales accessible to cosmic ray physics, potentially opening an entirely new window into fundamental physics that complements the searches being conducted at particle accelerators like the Large Hadron Collider. Perhaps the most mind-bending explanation for the ANITA anomaly involves the possibility of a mirror universe, a parallel reality where the laws of physics operate in reverse. This idea, while sounding like science fiction, emerges from serious theoretical considerations in cosmology and particle physics. The mirror universe hypothesis suggests that our cosmos might be paired with an anti-universe where time runs backward, antimatter dominates over matter, and physical processes unfold in reverse. Under certain conditions, particles from this mirror reality might interact with our own universe, creating signatures that could be detectable by sensitive instruments. In this scenario, the upward-going signals that Anita detected might not represent particles traveling through Earth at all, but rather mirror particles from the parallel universe that briefly interact with our reality before disappearing back into their own realm. The apparent violation of energy conservation and causality would be resolved by recognizing that we're observing the intersection of two universes rather than impossible physics within our own. This explanation has gained attention from theorists because it could potentially solve several cosmological puzzles simultaneously. The mirror universe could help explain the observed matter-antimatter asymmetry in our cosmos, provide a candidate for dark matter, and even offer insights into the nature of time itself. Another exotic possibility involves quantum tunneling, the strange quantum mechanical phenomenon that allows particles to pass through barriers that should be impenetrable according to classical physics. In the quantum world, there's always a small probability that a particle can tunnel through any barrier, no matter how substantial. On microscopic scales, quantum tunneling is well understood and practically exploited in technologies like electron microscopes and semiconductor devices. But could similar effects operate on the vast scale of planetary interiors? Some theoretical models suggest that under extreme conditions, such as the ultra-high energies involved in the Anita events, quantum tunneling might become significant even for macroscopic distances. If cosmic-scale quantum tunneling is real, it might allow high-energy particles to occasionally skip through Earth's interior as if the planet were partially transparent. This could explain how neutrinos or other particles manage to traverse thousands of kilometers of dense rock and metal while maintaining energies that should guarantee their absorption. The most speculative explanations for the Anita anomaly invoke concepts from string theory and theories of extra dimensions. These advanced theoretical frameworks suggest that our three-dimensional space might be embedded in a higher dimensional reality, with additional spatial dimensions that are too small or too warped for us to perceive directly. In some models, high-energy particles might be able to leak into these extra dimensions, taking shortcuts through higher dimensional space that allow them to appear on the opposite side of Earth without actually traveling through the planet's interior. Such particles might occasionally return to our three-dimensional world, creating the upward-going signals that Anita observed. While these explanations stretch the boundaries of current scientific understanding, they emerge from mathematically sophisticated theories that attempt to unify all the fundamental forces of nature. If any of these exotic phenomena are responsible for the Anita anomaly, the discovery would represent one of the most profound breakthroughs in the history of physics. The challenge facing physicists is determining which, if any, of these extraordinary explanations might be correct, or whether the truth lies in territory so unexplored that we don't yet have the theoretical tools to understand it. The question haunts every discussion of the Anita anomaly: why Antarctica? Why would signals that potentially challenge the foundations of physics emerge from this specific frozen continent at the bottom of the world? The answer may lie not just in Antarctica's practical advantages as a scientific platform, but in its unique position as a natural focal point for cosmic phenomena we're only beginning to understand. Antarctica's scientific appeal begins with simple geography and geology. The continent sits atop a bedrock foundation that differs significantly from other landmasses, with unique mineral compositions and geological structures that have been shaped by millions of years of isolation. The thick ice sheet, averaging 2.16 kilometers deep and reaching over 4.8 kilometers at its thickest point, creates conditions found nowhere else on Earth. This ice isn't uniform. Layers formed over hundreds of thousands of years create a complex, stratified structure with varying densities, trapped air bubbles, and inclusions of dust and other materials. The ice's optical and radio properties change with depth, potentially creating natural lenses or waveguides that could focus or amplify certain types of signals. The continent's position also matters. Antarctica sits roughly centered over the South Pole, meaning any particles traveling through Earth from the opposite hemisphere must pass through the planet's core before emerging in the Antarctic region. This geometry could concentrate certain types of cosmic phenomena in ways that wouldn't occur at other latitudes. Earth's magnetic field plays a crucial role in shaping how cosmic particles interact with our planet. The field lines converge at the magnetic poles, creating conditions that can trap, accelerate, or deflect charged particles in complex ways. Antarctica sits near one of these magnetic focal points, potentially making it uniquely sensitive to certain types of cosmic phenomena. Some theoretical models suggest that the magnetic field configuration over Antarctica could create natural particle accelerators in the upper atmosphere, where cosmic rays undergo unusual interactions that don't occur elsewhere. These interactions might produce exotic particles or energy distributions that could explain the anomalous signals ANITA detected. The magnetic field also affects how radio waves propagate through the atmosphere and ionosphere. The unique field geometry over Antarctica could create propagation conditions that allow signals to travel paths impossible at other locations, potentially explaining some of the directional anomalies in the ANITA data. If we accept the possibility that the ANITA signals represent something genuinely exotic, sterile neutrinos, supersymmetric particles, or interactions with parallel universes, then Antarctica's role becomes even more intriguing. The continent might serve as a natural window where these normally hidden phenomena become visible to our instruments. This idea isn't entirely without precedent in physics. Certain quantum field theories predict that interactions between different types of universes or dimensional branes might be enhanced at specific locations where geometric or topological conditions are favorable. If our universe is indeed part of a larger multiverse structure, certain places might serve as natural intersection points where phenomena from other realities occasionally leak through. Antarctica's isolation from human activity might also play a role. The continent has the lowest electromagnetic noise levels on Earth, making it possible to detect faint signals that would be overwhelmed by interference elsewhere. If exotic physics produces only very weak signatures, Antarctica might be the only place on Earth where they're detectable above the background. Throughout history, Antarctica has been associated with the unknown and mysterious. Ancient maps showed hints of southern continents long before any explorer had ventured into polar waters. Early Antarctic expeditions reported strange phenomena, unusual auroras, magnetic anomalies, and atmospheric effects that couldn't be explained by the science of their time. Modern Antarctica continues to surprise scientists. The continent hosts unique ecosystems in its subglacial lakes, contains evidence of ancient climate changes that have rewritten our understanding of Earth's history, and serves as a window into cosmic phenomena ranging from cosmic microwave background radiation to high-energy particle physics. The ANITA anomaly fits into this pattern of Antarctic surprise. Just as the continent has revealed unexpected biological, geological, and climatological phenomena, it may now be revealing new physics that exists nowhere else, or at least nowhere else where we have the instruments to detect it. The mystery of Antarctica's role in the ANITA anomaly may soon be clarified by PUEO, Payload for Ultra-High Energy Observations. ANITA's much more sophisticated successor, approved by NASA in 2021 with a $20 million budget, PUEO is designed to have 10 times the sensitivity of ANITA, with improved directional resolution and better background rejection. PUEO's enhanced capabilities could definitively determine whether the Anita anomaly represents genuine new physics or some subtle instrumental or environment effect unique to Antarctic conditions. If the signals are real and represent exotic physics, PUEO should detect many more such events, providing the statistical power needed to understand their true nature. Dr. Whistle, who is working on the PUEO project, expresses cautious optimism. So, right now, it's one of these long-standing mysteries, and I'm excited that when we fly PUEO, we'll have better sensitivity. In principle, we should pick up more anomalies, and maybe we'll actually understand what they are. If PUEO confirms that Antarctica is indeed a special place where new physics becomes visible, it could transform our understanding not just of particle physics, but of how different regions of Earth might serve as natural laboratories for exploring the deepest mysteries of the cosmos. The frozen continent might prove to be not just a repository of Earth's climate history, but a gateway to understanding realities beyond our current comprehension. When faced with phenomena that seem to violate the fundamental laws of physics, science sometimes finds itself compelled to consider the most radical possibilities imaginable. The persistent mystery of the Anita signals has led some of the world's most respected theoretical physicists to seriously examine one of the most mind-bending concepts in modern cosmology, the multiverse. Could these upward-traveling particles be messages from another universe entirely? The idea that our universe might be one of many isn't new to physics. It emerged naturally from quantum mechanics in the 1950s when physicists grappled with the strange behavior of particles at the smallest scales. Hugh Everett III proposed that rather than particles existing in fuzzy superposition states that collapse when observed, perhaps every possible outcome of quantum events actually occurs, but in separate parallel universes. This many-worlds interpretation suggests that reality constantly branches into countless parallel timelines. Every quantum measurement, every radioactive decay, every subatomic interaction creates new universes where different outcomes unfold. In some of these universes, you decided to have coffee instead of tea this morning. In others, dinosaurs never went extinct. In still others, the laws of physics themselves might operate differently. While this interpretation remains controversial among physicists, it has gained credibility as our understanding of quantum mechanics has deepened. If the many-worlds interpretation is correct, then our observable universe represents just one branch of an infinite tree of parallel realities. A different path to the multiverse comes from cosmology and our understanding of the Big Bang, the theory of cosmic inflation, which explains many observed features of our universe, suggests that space underwent a period of exponential expansion in the first fraction of a second after the Big Bang. This inflation might have created not just our universe but countless others, bubble universes that formed as different regions of space-time inflated at different rates. Each bubble universe could have different physical constants, different numbers of dimensions, even different types of particles and forces. Most would be completely isolated from each other, separated by vast regions of eternally inflating space-time. But occasionally, under very special circumstances, these bubbles might collide or interact, potentially leaving detectable signatures in the cosmic microwave background radiation or other observable phenomena. Could the Anita signals represent evidence of such bubble universe interactions? Some theoretical models suggest that collisions between cosmic domains could produce exotic particles or energy flows that might manifest as anomalous signals in sensitive detectors. If our universe is indeed part of a vast multiverse structure, Antarctica might be positioned at a particularly sensitive location where such interdimensional interactions become detectable. Perhaps the most intriguing multiverse explanation for the Anita anomaly involves the concept of a mirror universe. Not just any parallel reality, but one that operates as a precise mirror image of our own. This idea has gained serious attention from cosmologists because it could solve several fundamental puzzles about the nature of our cosmos. In standard Big Bang cosmology, we face the mystery of why our universe contains more matter than antimatter. If the laws of physics are symmetric, the Big Bang should have produced equal amounts of both, which would have annihilated each other completely, leaving behind only radiation. Yet here we are, made of matter, in a universe filled with matter-dominated galaxies. The mirror universe hypothesis suggests that the Big Bang actually did produce equal amounts of matter and antimatter, but they were separated into two distinct universes. Our universe became matter-dominated, while its mirror twin became antimatter-dominated. More intriguingly, if the symmetry is complete, time might run backward in the mirror universe relative to our own. This creates a fascinating possibility. Particles from the mirror universe might occasionally cross over into our reality, appearing to travel backward in time from our perspective. When Anita detected particles that seemed to emerge from deep within Earth, it might actually have been observing mirror universe particles that crossed dimensional boundaries, briefly manifesting in our reality before disappearing back into their own. Recent advances in quantum mechanics have revealed the strange phenomenon of quantum entanglement, where particles become interconnected in ways that seem to defy classical logic. Entangled particles instantly affect each other regardless of the distance separating them, a connection Einstein famously dismissed as spooky action at a distance, but which has now been confirmed by countless experiments. Some theoretical physicists have speculated that quantum entanglement might operate not just across space, but across the boundaries between parallel universes. If particles in our universe became entangled with particles in other realities, interactions in one universe might produce detectable effects in another. This interdimensional entanglement could provide a mechanism for the Anita signals. High-energy cosmic ray interactions in parallel universes might occasionally produce quantum effects that manifest as particle detections in our own reality. The apparent violation of energy conservation and causality would be resolved by recognizing that we're observing the effects of events happening in other universes. The challenge with multiverse explanations is that they seem inherently untestable. How can we observe other universes from within our own? However, some theoretical models do make specific predictions that could potentially be verified or falsified. If the Anita signals represent interdimensional particle crossings, they should show certain statistical patterns related to the quantum mechanical processes that govern such interactions. The energy distributions, arrival times, and directional properties of the signals might encode information about the nature of the parallel universes they originated from. Advanced analysis of the Anita data combined with observations from PUEO and other next-generation experiments might be able to distinguish between multiverse explanations and more conventional exotic physics. Computer simulations of interdimensional interactions could generate predictions that can be compared with the observed anomalies. If the Anita signals do represent evidence of a multiverse, the implications extend far beyond particle physics. Such a discovery would fundamentally alter our understanding of reality itself, suggesting that our universe, with all its galaxies, stars, planets, and life, represents just one note in an infinite symphony of parallel realities. The concept challenges our most basic assumptions about existence, causality, and the nature of physical law. If multiple universes exist with different physical constants and different histories, questions about why our universe seems fine-tuned for the existence of complexity and life take on entirely new dimensions. Perhaps most profoundly, multiverse physics might provide scientific grounding for age-old philosophical questions about the nature of consciousness, free will, and the relationship between mind and reality. If every possible outcome of every quantum event creates new universes, then somewhere in the multiverse, every possible version of history is unfolding simultaneously. The strange radio signals emerging from Antarctic ice might thus represent far more than just another physics anomaly. They could be our first glimpse into the vast hidden architecture of reality itself, proof that our universe is not alone, but part of an infinite tapestry of parallel worlds, each as real and complex as our own. The Anita anomaly has triggered one of the most intensive international scientific collaborations of the modern era. As news of the impossible signals spread through the global physics community, researchers from dozens of countries began mobilizing resources, expertise, and instruments in an unprecedented effort to understand what might be one of the most significant discoveries in the history of science, or one of the most persistent experimental mysteries. The first major response came from the IceCube Neutrino Observatory, the massive particle detector embedded deep in the Antarctic ice near the South Pole. IceCube represents one of the most ambitious scientific instruments ever constructed. A cubic kilometer of ice instrumented with over 5,000 optical sensors designed to detect the faint flashes of light produced when neutrinos interact with frozen water molecules. If the Anita signals represented genuine ultra-high energy neutrinos traversing Earth, IceCube should have been ideally positioned to observe similar events. The collaboration launched an intensive analysis of their archived data, searching for any evidence of upward-going neutrino events that might corroborate Anita's observations. The results were sobering. Despite analyzing over 300,000 neutrino detections collected over 8 years of operation, IceCube found no evidence of the anomalous upward-going events that Anita had reported. This null result didn't disprove the Anita observations, but it placed significant constraints on any explanation involving conventional or exotic neutrinos. Dr. Francis Halzen, the principal investigator of IceCube, noted the implications. IceCube's sensitivity to upward-going neutrinos at the energies Anita detected should have allowed us to observe multiple similar events if they represent a general phenomenon. The absence of such detections suggests that either the Anita events are extremely rare, represent a different type of particle entirely, or result from processes specific to Anita's balloon-borne detection method. Halfway around the world in Argentina, the Pierre Auger Observatory, the largest cosmic ray detector ever built, launched its own investigation. Covering an area of 3,000 square kilometers with an array of particle detectors and fluorescence telescopes, Auger has been monitoring cosmic ray showers since 2004, accumulating one of the most comprehensive datasets of high-energy particle interactions in Earth's atmosphere. The Auger Collaborations Analysis, published in Physical Review Letters in 2025, examined 15 years of data for any evidence of anomalous upward-going air showers similar to those reported by Anita. The search was exhaustive, applying the same energy thresholds and directional criteria that Anita had used to identify its anomalous events. The results mirrored IceCube's findings, no evidence of similar anomalous events in the Auger dataset. This null result from an independent detector using a completely different detection technology further complicated efforts to explain the Anita signals through conventional physics. The Anita mystery has also mobilized research groups across Europe and Asia. The Antares Neutrino Telescope in the Mediterranean Sea, while optimized for different energy ranges than Anita, has contributed analysis of its data for any potential correlation with the Antarctic observations. Radio astronomy facilities across Europe have examined whether similar signals might be detectable from other locations on Earth. In Japan, the Super Kamiokande detector and the newer Hyper Kamiokande project have incorporated Anita-related research into their scientific programs. Japanese researchers have also contributed theoretical work on exotic particle physics models that might explain the anomalous signals. Chinese institutions have launched computational initiatives to model the propagation of various hypothetical particles through Earth's interior, testing whether any known or theoretical particle physics could account for the Anita observations. These massive computer simulations have examined everything from sterile neutrinos to supersymmetric particles to quantum tunneling effects. Beyond experimental efforts, the Anita anomaly has spawned a renaissance in theoretical particle physics. Researchers at institutions worldwide have published hundreds of papers exploring potential explanations, ranging from modest extensions of the Standard Model to radical new theories involving extra dimensions and parallel universes. The Fermi National Accelerator Laboratory, Fermilab, has established working groups dedicated to ANITA-related research, bringing together theorists and experimentalists to develop testable models for the anomalous signals. Similar efforts are underway at CERN, the European Centre for Nuclear Research, where physicists are exploring whether the Large Hadron Collider might be able to produce or detect particles similar to those implicated in the ANITA events. The global response to ANITA has accelerated development of next-generation particle detection experiments. Beyond PUEO, several other ambitious projects have been proposed or are under development. The Warmsch Radio Neutrino Observatory, RNO, combines surface and deep ice-based radio detectors to provide unprecedented sensitivity to ultra-high energy neutrinos. The WAM Grand, giant radio array for neutrino detection. Project envisions arrays of radio antennas covering thousands of square kilometers, designed to detect cosmic neutrinos and potentially anomalous events like those ANITA observed. These projects represent investments of hundreds of millions of dollars and involve collaborations among dozens of institutions worldwide. The scale of this response demonstrates the profound impact the ANITA anomaly has had on the global physics community. The complexity of the ANITA mystery has necessitated unprecedented levels of international coordination. The International Committee for Future Accelerators, ICFA, has established working groups to coordinate global efforts to understand the anomaly. Regular international workshops bring together experimentalists and theorists to share data, compare analyses, and develop unified approaches to testing various hypotheses. This collaborative approach has been essential because the ANITA anomaly intersects multiple subfields of physics: particle physics, cosmic ray physics, neutrino astronomy, theoretical physics, and even cosmology. No single institution or even single country has all the expertise and resources needed to fully investigate the phenomenon. The global scientific response to ANITA demonstrates both the strength of modern international scientific collaboration and the profound implications of the anomaly itself. When faced with observations that challenge the foundations of physics, the worldwide scientific community has marshaled its resources in an unprecedented effort to understand what might be one of the most important discoveries of the 21st century. Science demands replication. A single experiment, no matter how carefully conducted, cannot stand alone when claiming to have discovered new physics. The ANITA anomaly has therefore triggered an urgent international search for corroborating evidence. Other experiments, different detection methods, and independent observations that might confirm or refute the impossible signals emerging from Antarctic ice. The search for corroboration faces unique challenges. Unlike laboratory experiments that can be repeated under controlled conditions, the ANITA observations occurred in the wild, unpredictable environment of Antarctica, using a one-of-a-kind balloon-borne detector flying at extreme altitude. The specific combination of factors, the detector's position, orientation, and sensitivity, combined with Antarctic atmospheric and ice conditions, may be impossible to replicate exactly. This challenge is compounded by the extreme rarity of the events themselves. ANITA operated for a total of approximately 100 days across its 4 flights between 2006 and 2016. During which it detected only a handful of anomalous events. If these signals represent real physics phenomena occurring at such low rates, detecting them with other instruments might require years or decades of observation. The most direct approach to corroboration involves searching for similar signals in other neutrino detectors around the world. The IceCube collaboration has conducted the most thorough such search, analyzing their complete data set for events that might match the ANITA anomaly's characteristics. IceCube's analysis methodology was painstaking. Researchers examined over 300,000 neutrino candidate events, applying filters designed to identify upward-going particles with energies and directional properties similar to those Anita observed. They searched for correlations with Anita's observation time, examined the energy spectra of their most energetic events, and looked for any statistical anomalies that might suggest the presence of exotic physics. The absence of clear corroborating signals in IceCube's data has been one of the most significant challenges to accepting the Anita anomaly as evidence of new physics. However, some researchers argue that the different detection methods used by the two experiments might explain this discrepancy. Anita detects radio waves produced by particle interactions in ice, while IceCube detects optical photons produced by particles moving through ice. It's possible that whatever process produces the Anita signals might not generate the optical signatures that IceCube is designed to detect. Ground-based cosmic ray observatories provide another potential source of corroborating evidence. The Pierre Auger Observatory's recent analysis represents the most comprehensive such search to date. With its vast array of surface detectors and fluorescence telescopes covering 3,000 square kilometers, Auger has observed millions of cosmic ray events over its 15-year operational history. The collaboration's search for Anita-like events involved sophisticated data mining techniques, examining their archived observations for any evidence of anomalous upward-going air showers. They applied machine learning algorithms to identify events with unusual directional or energy characteristics that might have been missed in previous analyses. The null result from Auger has been interpreted differently by various research groups. Some see it as strong evidence against the reality of the Anita anomaly, arguing that if such events were genuine manifestations of new physics, they should be detectable by multiple different types of experiments. Others contend that the different detection methods and geographic locations might explain the absence of correlating signals. The search for corroboration has extended beyond ground-based detectors to space-based instruments and atmospheric monitoring systems. NASA's Fermi Gamma Ray Space Telescope has been enlisted to search for high-energy gamma rays that might be associated with whatever process produces the Anita signals. Atmospheric monitoring stations across Antarctica have examined their data for unusual radio frequency emissions that might correlate with Anita's anomalous events. These searches have looked for evidence of atmospheric disturbances, unusual ionospheric activity, or other environmental factors that might either explain the signals through conventional processes or provide additional evidence for exotic physics. Radio astronomy facilities worldwide have joined the search for Anita-like signals. The Very Large Array in New Mexico, the Atacama Large Millimeter Array in Chile, and radio telescopes across Europe and Asia have examined their archived data for transient radio signals with characteristics similar to those Anita detected. These searches face the challenge that most radio telescopes are optimized for astronomical observations rather than particle detection, making them less sensitive to the brief, broadband pulses that characterize neutrino interactions. However, their global distribution and continuous operation make them valuable for detecting any widespread phenomenon that might be related to the Anita anomaly. The search for corroboration has been complicated by statistical considerations. The Anita events are so rare that even if they represent genuine physics phenomena, the probability of detecting them with other instruments during overlapping observation periods might be extremely low. Researchers have developed sophisticated statistical models to determine how many corroborating detections would be needed to confirm the Anita anomaly with high confine dense. These calculations suggest that dozens or even hundreds of similar events might be required across multiple independent experiments before the scientific community would be convinced that new physics has been discovered. The absence of clear corroboration has not disproven the Anita anomaly. but it has significantly raised the bar for acceptance. The next phase of the investigation will likely depend on PUEO and other next-generation experiments that are specifically designed to have the sensitivity and directional resolution needed to definitively test whether the impossible signals from Antarctica represent genuine new physics or some subtle systematic effect that has thus far eluded explanation. In the world of experimental physics, when an anomaly refuses to disappear and conventional explanations fail, the next step is clear: build a better detector. The mystery of Anita's impossible signals has motivated exactly such an effort, culminating in PUEO, Payload for Ultra-High Energy Observations, a next-generation experiment that promises to either solve the Antarctic puzzle once and for all, or confirm that we're witnessing something truly revolutionary. PUEO represents a quantum leap in experimental capability compared to its predecessor, approved by NASA in 2021 with a $20 million budget. https://news.uchicago edu story/find energetic particles space new detector will soar over Antarctic ice. The project brings together an international collaboration of institutions including the University of Chicago, Penn State, Ohio State University, the University of Hawaii, and several other leading research universities. The technical specifications of PUEO are impressive by any measure. The detector will feature over 200 radio antennas arranged in a sophisticated array designed to provide unprecedented directional sensitivity and background rejection. Where Anita's antennas were relatively simple dipole designs, PUEO will employ advanced phased array technology that can electronically steer its sensitivity pattern and reject interference from unwanted sources. Perhaps most importantly, PUEO will have approximately 10 times the sensitivity of Anita. This improvement comes from multiple factors: more antennas, better electronics, improved signal processing, and advanced triggering systems that can identify potential neutrino events in real time while rejecting the vast majority of background signals that plagued earlier experiments. The heart of PUEO's enhanced capability lies in its sophisticated electronics and data processing systems. Modern digital signal processing techniques, unavailable when Anita was first designed, allow PUEO to perform complex, real-time analysis of incoming signals. The detector can simultaneously search for multiple types of events, not just the tau neutrino signatures that Anita targeted, but also electron neutrinos, exotic particles, and even unknown phenomena that might not fit any theoretical prediction. PUEO's improved directional resolution is particularly crucial for understanding the Anita anomaly. Where Anita could determine the arrival direction of signals to within a few degrees, PUEO will achieve sub-degree precision. This enhanced accuracy will be essential for distinguishing between signals that truly come from below the ice and those that might result from complex atmospheric reflection or refraction effects. The experiment will also feature unprecedented energy resolution, allowing researchers to measure the energies of detected particles with much greater precision than Anita achieved. This capability could provide crucial clues about the nature of any anomalous events, as different theoretical explanations predict different energy spectra and characteristics. PUEO has been specifically designed to address the key questions raised by the Anita anomaly. If the upward-going signals represent genuine new physics, PUEO should detect them at a rate roughly 10 times higher than Anita observed, providing the statistical power needed to characterize their properties in detail. Dr. Abigail Viereg of the University of Chicago, PUEO's principal investigator, emphasizes the experiment's potential. PUEO will either confirm that these anomalous events are real and provide us with enough statistics to understand what they are, or it will show us that they were some kind of systematic effect that we didn't understand in Anita, The experiment's enhanced capabilities should also allow it to distinguish between the various theoretical explanations that have been proposed for the Anita signals. Sterile neutrinos, supersymmetric particles, and interdimensional phenomena would each produce characteristic signatures that PUEO should be able to detect and differentiate. PUEO is scheduled to launch from Antarctica in December 2024 following the successful Southern Hemisphere launch seasons that have become standard for Antarctic balloon experiments. The payload will be carried to an altitude of approximately 37 kilometers by a NASA ultra-long-duration balloon, similar to those used for Anita but with improved stability and duration capabilities. The experiment is designed to operate for up to 100 days during the Antarctic summer, circling the continent multiple times while continuously monitoring for neutrino interactions in the ice below. This extended operation period will provide PUEO with significantly more observation time than any single Anita flight achieved. Advanced telemetry systems will allow researchers to monitor PUEO's performance in real time and even modify its operational parameters during flight. This capability could prove crucial if the experiment begins detecting anomalous events similar to those Anita observed, allowing scientists to optimize the detector's configuration to maximize the scientific return. While much attention has focused on PUEO's potential to solve the Anita mystery, the experiment has broader scientific goals that could revolutionize our understanding of the highest energy phenomena in the universe. Ultra-high energy neutrinos represent messengers from the most extreme environments in the cosmos, the vicinity of supermassive black holes, the cores of active galactic nuclei, and perhaps the sites of dark matter annihilation. PUEO's enhanced sensitivity should allow it to detect conventional ultra-high energy neutrinos for the first time, opening a new window into high-energy astrophysics. These observations could help solve long-standing puzzles about the sources of the highest energy cosmic rays and provide insights into physics at energy scales that no terrestrial accelerator can achieve. The experiment will also serve as a technology demonstrator for even more ambitious future projects. The radio detection techniques pioneered by Anita and refined by PUEO could eventually be scaled up to create massive neutrino observatories covering thousands of square kilometers, potentially revolutionizing our ability to study the high-energy universe. The stakes for PUEO could hardly be higher. If the experiment confirms the Anita anomaly, it will mark one of the most significant discoveries in the history of physics, potentially revealing new fundamental particles, extra dimensions, or even evidence of parallel universes. If it fails to detect similar signals, it will likely close the book on one of the most tantalizing mysteries in modern science, forcing physicists to conclude that the Anita events resulted from some subtle systematic effect that is now understood. Dr. Stephanie Wissel, involved in both Anita and PUEO, captures the anticipation. I'm excited that when we fly PUEO, we'll have better sensitivity. In principle, we should pick up more anomalies, and maybe we'll actually understand what they are. We also might detect neutrinos, which would in some ways be a lot more exciting. As PUEO prepares for its Antarctic journey, the international physics community waits with bated breath. The next chapter in the story of the strange radio signals from Antarctica is about to be written, and it could change our understanding of reality itself. The hunt for the source of Anita's anomalous signals has sparked a technological revolution in particle detection that extends far beyond the Antarctic ice. The challenge of detecting and understanding these elusive phenomena has driven innovations in radio astronomy, signal processing, and data analysis that are finding applications across multiple fields of science and technology. The Anita experiment marked a pivotal moment in the renaissance of radio detection techniques for particle physics. While radio astronomy has long been a sophisticated field, using radio waves to detect individual particle interactions represented a relatively new and challenging application. The success of ANITA in detecting neutrino-like signals through radio emissions has validated this approach and inspired a new generation of radio-based particle detectors. The fundamental principle underlying radio neutrino detection, the Askaryan effect, was first predicted theoretically in 1962 by Soviet physicist Gurgen Askaryan. When a high-energy particle creates a cascade of secondary particles in a dense medium like ice, the cascade develops a slight charge asymmetry due to electrons being knocked out of atoms more readily than positively charged particles. This moving charge distribution generates coherent radio waves that can be detected from distances of several kilometers. ANITA demonstrated that this effect could be exploited on a practical scale, leading to rapid development of similar radio detection systems worldwide. The technique offers several advantages over traditional particle detection methods. Radio waves can travel long distances through ice and rock with minimal absorption. Radio antennas can cover vast areas at relatively low cost, and the coherent nature of Askaryan radiation makes it easier to distinguish from background noise. The challenge of extracting genuine particle signals from the complex radio noise environment has driven remarkable advances in digital signal processing. Modern experiments like PUEO employ sophisticated algorithms that can analyze incoming radio signals in real time, making split-second decisions about which events might represent genuine particle interactions. These processing systems must cope with extraordinary data rates. A typical radio neutrino detector might sample hundreds of antennas at rates of several gigahertz, generating terabytes of data per day. Advanced machine learning algorithms, originally developed for applications like image recognition and natural language processing, have been adapted to identify the subtle patterns that might distinguish neutrino signals from background interference. The signal processing innovations developed for neutrino detection have found applications in other fields. Similar techniques are being used to improve weather radar systems, enhance communications in challenging environments, and even search for signals from extraterrestrial civilizations. The algorithms developed to distinguish genuine particle signals from background noise have proven remarkably effective at extracting weak signals from noisy environments in many different contexts. The demanding requirements of Antarctic balloon experiments have driven significant advances in high-altitude balloon technology. The balloons used for ANITA and PUEO must carry multi-ton payloads to stratospheric altitudes, maintain stable flight paths for weeks or months, and operate reliably in the extreme cold and variable winds of the Antarctic environment. Modern ultra-long-duration balloons represent marvels of engineering. They use advanced polymer films that can withstand the extreme temperature cycles of day and night at stratospheric altitudes, where temperatures can swing from 80 degrees Celsius to 40 degrees Celsius within a few hours. Sophisticated ballast and attitude control systems allow these balloons to maintain precise altitudes and orientations despite changing atmospheric conditions. The power systems for these experiments have also evolved dramatically. Early balloon experiments relied on simple battery systems that limited flight durations to days or weeks. Modern experiments like PUEO use advanced solar panel arrays and battery management systems that can provide continuous power for months of operation, even during the extended periods of reduced sunlight that occur during Antarctic flights. Perhaps the most significant technological impact of the ANITA mystery has been in the realm of data analysis. The challenge of understanding these anomalous signals has pushed researchers to develop new statistical methods, visualization techniques, and collaborative analysis frameworks that are transforming how large-scale scientific experiments are conducted. Traditional particle physics experiments often deal with millions or billions of events, but the statistical methods used to analyze them were developed for much smaller datasets. The ANITA anomaly, based on just a handful of events observed over years of operation, has forced statisticians and physicists to develop new approaches for extracting meaningful conclusions from rare phenomena. Bayesian statistical methods, Monte Carlo simulation techniques, and machine learning approaches have all been refined and enhanced through their application to the ANITA dataset. These improved methods are now being applied to other rare event searches in physics, from dark matter detection to gravitational wave astronomy. The global effort to understand the ANITA anomaly has also driven innovations in scientific collaboration infrastructure. Researchers from dozens of institutions across multiple continents must share data, coordinate analyses, and develop common interpretation frameworks. This has led to new approaches for managing distributed scientific collaborations and sharing sensitive research data. Cloud computing platforms specifically designed for scientific applications have emerged from this need. These systems allow researchers worldwide to access the same datasets, run consistent analysis codes, and share results in real time. The collaborative analysis techniques developed for ANITA are now being adopted by other large-scale scientific projects, from climate research to genomics. The technological innovations sparked by the ANITA mystery continue to evolve. Next-generation radio detection arrays like the proposed GRAND Giant Radio Array for neutrino detection project in vision covering thousands of square kilometers with networks of radio antennas, creating neutrino telescopes of unprecedented sensitivity. These future experiments will incorporate artificial intelligence systems that can autonomously recognize interesting events, adaptive signal processing that can modify detection parameters in real time based on changing conditions, and distributed computing systems that can process and analyze data from thousands of detectors simultaneously. The strange radio signals from Antarctica have thus catalyzed a technological revolution that extends far beyond their original mystery. Regardless of whether these signals ultimately prove to represent new physics or subtle instrumental effects, they have driven innovations that are transforming how we explore the universe and understand the fundamental nature of reality. The ANITA anomaly has captured public imagination in ways that few scientific mysteries have achieved. From sensational headlines about parallel universes to serious science documentaries exploring the implications of new physics, the story of strange radio signals emerging from Antarctic ice has resonated far beyond the academic world, sparking widespread fascination with fundamental questions about the nature of reality. The journey from peer-reviewed scientific publication to global media phenomenon began in 2016 when the ANITA collaboration first published their observations of anomalous upward-going events. Initially, the scientific community responded with appropriate caution, recognizing that extraordinary claims require extraordinary evidence. But as additional analysis confirmed the persistence of the anomaly and ruled out conventional explanations, media attention began to build. The transformation of the story from scientific mystery to public fascination accelerated dramatically in 2020 when several theoretical papers suggested that the ANITA signals might represent evidence of a mirror universe or parallel dimension. Headlines around the world proclaimed that NASA had discovered a parallel universe where time runs backward, often oversimplifying or sensationalizing the actual scientific claims. While many scientists expressed frustration with the media's tendency toward hyperbole, the intense public interest served an important purpose. It brought fundamental questions about particle physics and cosmology to the attention of millions of people who might otherwise never encounter such concepts. The ANITA story became a gateway for public engagement with cutting-edge science. The parallel universe interpretation of the ANITA data proved particularly captivating to public imagination. The idea that our universe might be paired with a mirror reality, where time flows backward and antimatter dominates, appeals to deep human fascinations with hidden worlds and alternative realities that have inspired science fiction for generations. Social media platforms amplified this fascination, with viral posts explaining the theory in simplified terms and speculating about its implications. YouTube videos exploring the NASA parallel universe discovery garnered millions of views, while podcasts and online forums buzzed with discussions about the meaning of the findings. The popularity of this interpretation also highlighted a persistent challenge in science communication: the gap between the nuanced, probabilistic language of scientific papers and the definitive, dramatic narratives that capture public attention. While scientists spoke carefully about possible interpretations and intriguing hypotheses, headlines proclaimed the discovery of a parallel universe. Despite the sensationalism, the public fascination with the Anita anomaly has created unprecedented opportunities for science education. Physics teachers and science communicators have used the story as a hook to explain fundamental concepts about particle physics, the Standard Model, and the scientific method. The mystery has proven particularly effective for demonstrating how science actually works, not through sudden eureka moments, but through careful observation, rigorous analysis, and the gradual accumulation of evidence. Students can follow the ongoing investigation in real time, seeing how scientists form hypotheses, design experiments to test them, and modify their understanding based on new data. Universities have reported increased enrollment in physics courses, with many students citing their fascination with the Anita mystery as a motivating factor. The story has shown that fundamental physics isn't just abstract mathematics, but an active field where new discoveries might revolutionize our understanding of reality. The Anita anomaly has also influenced popular culture in surprising ways. Science fiction authors have incorporated ideas inspired by the mystery into their work, exploring fictional scenarios where interdimensional particles provide communication channels between parallel universes, or where Antarctic ice serves as a natural portal to other realities. Documentary filmmakers have produced several high-profile programs about the mystery, often focusing on the human drama of scientists grappling with observations that challenge everything they thought they understood about physics. These productions have helped humanize the scientific process, showing the excitement, frustration, and intellectual courage required to pursue revolutionary ideas. Artists and musicians have also drawn inspiration from the story. The concept of impossible signals from the bottom of the world has appeared in various forms across different media, from electronic music compositions that incorporate actual Anita data as sound to visual art installations, exploring themes of hidden realities and interdimensional communication. The intense public interest in the Anita anomaly has also highlighted the importance of scientific skepticism and critical thinking. As alternative explanations and null results from other experiments have emerged, science communicators have had to explain why the absence of corroborating evidence doesn't necessarily disprove the original observations, but does require adjusting confidence levels and considering more mundane explanations. This aspect of the story has provided valuable lessons about how science deals with uncertainty and how the strength of evidence affects scientific conclusions. The public has been able to observe in real time how the scientific community evaluates competing hypotheses and updates its understanding based on new information. As PUEOPRs, Icarus for launch and other next-generation experiments come online, public interest in the Anita mystery continues to grow. The story has demonstrated the public's hunger for authentic scientific mystery and their willingness to engage with complex ideas when they're presented in accessible ways. Science museums have developed exhibits about the Anita anomaly, allowing visitors to explore the concepts of particle physics and the scientific method through hands-on activities. Educational videos, online courses, and citizen science projects have emerged from the public fascination with the mystery. The Anita story has thus become more than just a scientific puzzle. It has evolved into a powerful tool for science education and public engagement, demonstrating that the most profound questions about the nature of reality can capture human imagination as powerfully as any work of fiction. If the Anita anomaly represents genuine new physics rather than experimental artifact, its implications extend far beyond particle physics into the deepest questions of cosmology. The strange signals emerging from Antarctic ice could force us to reconsider our understanding of the universe's structure, evolution, and fundamental nature in ways that might rival the revolutionary insights of Einstein's relativity or the discovery of cosmic expansion. Modern cosmology rests on a remarkably successful theoretical framework known as the lambda cold dark matter (LCDM) model. This elegant theory explains the universe's evolution from the Big Bang through cosmic inflation, the formation of the first atoms, the birth of stars and galaxies, and the current era of accelerating expansion driven by dark energy. The model's success is extraordinary. It accurately predicts the cosmic microwave background radiation's precise temperature fluctuations, explains the observed abundances of light elements like hydrogen and helium, accounts for the large-scale structure of galaxies and galaxy clusters, and describes the universe's current composition: approximately 5% ordinary matter, 27% dark matter, and 68% dark energy. Yet this successful model assumes that the fundamental laws of physics, particularly the standard model of particle physics, operate consistently throughout the universe and across cosmic time. If the Anita signals represent evidence of physics beyond the standard model, they could signal cracks in this cosmological edifice that might require fundamental reconstruction. One of the most intriguing possibilities is that the Anita anomaly might be connected to dark matter, the invisible substance that comprises over a quarter of the universe's mass energy content. Despite decades of searching, dark matter particles have never been directly detected, leading to increasingly exotic theoretical proposals for their nature and properties. If the Anita signals represent sterile neutrinos, this discovery could solve multiple cosmological puzzles simultaneously. Sterile neutrinos are leading candidates for dark matter particles, and their detection would provide the first direct evidence for the dark sector that dominates cosmic matter. Moreover, sterile neutrinos could help explain several anomalies in cosmic structure formation and the observed properties of dwarf galaxies. The connection runs deeper than simple particle identification. If sterile neutrinos exist and can travel through ordinary matter as easily as the Anita observations suggest, they might have played crucial roles in the early universe's evolution. During the first few minutes after the Big Bang, when ordinary matter was still too hot to form stable atoms, sterile neutrinos could have influenced the formation of the first structures and affected the process of Big Bang nucleosynthesis that produced the light elements. Perhaps the most radical cosmological implications arise if the Anita signals represent evidence of extra dimensions beyond the familiar three spatial dimensions plus time. String theory, our most ambitious attempt to unify all fundamental forces, requires additional spatial dimensions, typically 6 or 7, that must be compactified or hidden from direct observation. If high-energy particles can occasionally access these extra dimensions, as some interpretations of the Anita anomaly suggest, it would provide the first direct evidence for the higher dimensional structure that string theory predicts. This discovery would revolutionize cosmology by confirming that space itself has a far more complex geometry than we directly perceive. The implications extend to cosmic inflation, the period of exponential expansion that occurred in the universe's first fraction of a second. Many inflationary models rely on physics involving extra dimensions, and evidence for such dimensions from Anita would lend credibility to these scenarios. Moreover, if particles can travel through extra-dimensional shortcuts, it might explain certain fine-tuning problems in cosmology by allowing different regions of the universe to communicate through higher dimensional space. If the most exotic interpretations of the Anita anomaly prove correct, that the signals represent interactions with parallel universes, the cosmological implications would be revolutionary. The multiverse hypothesis has emerged from both quantum mechanics, the many worlds interpretation, and cosmic inflation theory, eternal inflation creating bubble universes. But direct evidence has remained elusive. Confirmation of interdimensional particle interactions would transform multiverse theories from philosophical speculation into testable science. If our universe can exchange particles with parallel realities, it suggests that the multiverse is not merely a theoretical construct, but a physical reality with measurable consequences. This discovery would force a complete reconceptualization of cosmic evolution. Instead of viewing our universe as an isolated system evolving according to its own physical laws, we would need to consider it as part of a vast multiverse network where interactions between parallel realities shape cosmic development in ways we've never imagined. The Anita anomaly might also challenge our understanding of the fundamental constants that govern physics. If the signals require new particles or forces to explain them, these discoveries could reveal that what we consider universal constants might actually vary across space, time, or between different regions of a larger multiverse. This possibility has profound implications for cosmic evolution. The precise values of fundamental constants like the fine structure constant, the mass of the electron, and the strength of the strong nuclear force appear to be fine-tuned for the existence of complex chemistry and life. If these constants can vary, it might explain this fine-tuning as a selection effect. We observe these particular values because they're necessary for our existence, while other regions of the multiverse with different constants remain sterile. If exotic particles like those possibly detected by Anita played roles in the early universe, they could have influenced the formation of cosmic structure in ways that might be observable today. Theoretical models suggest that interactions between ordinary matter and exotic particles could have affected the growth of density fluctuations that eventually became galaxies and galaxy clusters. Future cosmological surveys, like those planned for the Large Synoptic Survey Telescope and the European Space Agency's Euclid mission, might be able to detect subtle signatures of such exotic physics in the statistical properties of cosmic structure. The distribution of galaxies, the clustering of dark matter, and the evolution of cosmic voids might all carry imprints of the same physics that produces anomalous signals in Antarctic ice. Perhaps most philosophically profound are the implications for the anthropic principle. The observation that the universe's properties seem remarkably well-suited for the emergence of complexity and life. If the Anita anomaly represents evidence of a multiverse or extra dimensions, it could provide a natural explanation for cosmic fine-tuning without requiring design or extraordinary coincidence. In a multiverse where different regions have different physical laws and constants, the apparent fine-tuning of our universe becomes a selection effect rather than a mystery. We observe a life-friendly universe simply because that's the only type we could exist in to make the observation. This would represent a profound shift from viewing our universe as uniquely special to understanding it as one typical member of a vast ensemble of possible realities. The story of the strange radio signals from Antarctica thus connects intimately with the deepest questions of existence itself. Why is there something rather than nothing? Why do the laws of physics take the forms they do? Are we alone in the cosmos or part of something far grander than we've ever imagined? The Anita anomaly represents more than just a puzzle in particle physics. It embodies a crucial moment in the philosophy of science, where observation challenges theory and the scientific community grapples with fundamental questions about the nature of knowledge, evidence, and revolutionary discovery. The story illuminates how science actually progresses, not through smooth accumulation of facts, but through periods of crisis that ultimately transform our understanding of reality. The philosopher Thomas Kuhn revolutionized our understanding of scientific progress in his landmark work, The Structure of Scientific Revolutions. Kuhn argued that science doesn't advance through gradual, steady accumulation of knowledge, but through periodic paradigm shifts, fundamental changes in the basic assumptions and methods that define scientific fields. The Anita anomaly exhibits all the characteristics of what Kuhn called crisis science, the period when established paradigms begin to fail and the scientific community faces observations that cannot be easily incorporated into existing theoretical frameworks. The signals from Antarctica represent what Kuhn termed anomalies, phenomena that resist explanation within the current paradigm despite repeated attempts at resolution. During such crisis periods, Kuhn observed, scientists exhibit various responses. Some ignore or dismiss the anomalies, others attempt increasingly elaborate modifications to existing theories, while still others begin exploring radical alternatives that might eventually replace the current paradigm entirely. The response to Anita has demonstrated all these patterns, from skeptical dismissal to exotic multiverse theories. The Anita mystery also highlights what philosophers call the underdetermination of theory by data, the recognition that any given set of observations can potentially be explained by multiple incompatible theories. The same anomalous signals that some interpret as evidence of sterile neutrinos might be explained by others through atmospheric effects, instrumental artifacts, or entirely unknown physics. This underdetermination creates a fundamental challenge for scientific methodology. How should the scientific community respond when multiple explanations remain viable? The history of science suggests that such periods of uncertainty are often the most creative and productive, forcing researchers to develop new experimental techniques, theoretical frameworks, and standards of evidence. The Anita case demonstrates how scientific communities navigate this uncertainty through collective judgment, peer review, and the gradual accumulation of additional evidence. The process is neither purely objective nor entirely subjective, but represents a complex social and intellectual negotiation that ultimately shapes our understanding of reality. Scientific conservatism, the tendency to favor established theories over revolutionary alternatives, plays a crucial role in maintaining the stability and coherence of scientific knowledge. This conservatism isn't mere stubbornness, but serves important epistemological functions. It prevents science from being overwhelmed by false claims and ensures that revolutionary ideas must meet high standards of evidence before acceptance. The response to Anita demonstrates healthy scientific conservatism in action. The physics community has demanded rigorous testing of conventional explanations, sought independent replication, and maintained skepticism about exotic interpretations. This conservative response protects science from premature acceptance of revolutionary claims while ensuring that genuine discoveries eventually receive proper recognition. However, excessive conservatism can also impede scientific progress by dismissing genuinely revolutionary discoveries. The history of science includes numerous examples of important insights that were initially rejected by conservative scientific establishments, from continental drift to bacterial causes of ulcers to the expansion of the universe. Modern philosophy of science increasingly emphasizes Bayesian approaches to scientific reasoning, where scientists update their beliefs based on new evidence while accounting for prior probabilities and theoretical considerations. The Anita anomaly provides a perfect case study in how Bayesian reasoning operates in practice. Initia. Ellie. Most physicists assign very low prior probability to exotic explanations like parallel universes or new fundamental particles. The standard model has been so successful that alternatives seemed inherently unlikely. As evidence accumulated that conventional explanations couldn't account for the Anita signals, scientists began updating their probability assessments, though with significant variation in how much credence to assign to different hypotheses. The Bayesian framework helps explain why different scientists can examine the same evidence and reach different conclusions. Those with very strong priors favoring conventional physics require overwhelming evidence before accepting exotic alternatives, while others, more open to revolutionary possibilities, adjust their beliefs more readily based on suggestive data. The Anita story also illuminates how scientific knowledge is socially constructed through communities of researchers who collectively determine what counts as valid evidence, legitimate methodology, and acceptable explanation. The anomaly has sparked intense debate not just about physics, but about the standards and processes through which the scientific community evaluates extraordinary claims. This social dimension doesn't undermine scientific objectivity, but rather shows how objectivity emerges through collective scrutiny and criticism rather than individual insight. The global collaboration investigating Anita demonstrates how modern science transcends individual biases and limitations through distributed collaborative investigation. If the Anita anomaly ultimately proves to represent genuine new physics, it would join the ranks of great scientific revolutions that fundamentally altered human understanding of reality. The discovery of radioactivity revealed new forms of matter and energy. The theory of relativity transformed concepts of space and time, and quantum mechanics revolutionized understanding of causality and measurement. Each of these revolutions began with puzzling observations that didn't fit existing theory. The discovery of radioactivity emerged from investigations of mysterious rays emitted by uranium. Relativity originated from attempts to understand the null result of the Michelson-Morley experiment. Quantum mechanics arose from efforts to explain black-body radiation and atomic spectra. The Anita anomaly shares crucial characteristics with these historical precedents. Persistent observations that resist conventional explanation, implications that extend far beyond their immediate domain, and the potential to force fundamental reconceptualization of basic physical principles. The Anita investigation also highlights how scientific methodology itself evolves in response to new challenges. The combination of sophisticated statistical analysis, international collaboration, and real-time data sharing represents advances in scientific practice that enhance our ability to investigate complex phenomena. Machine learning algorithms, Bayesian statistical methods, and global collaboration networks developed for Anita research are already being applied to other scientific mysteries, from dark matter detection to the search for extraterrestrial intelligence. The methodological innovations sparked by the anomaly may prove as important as any specific discovery about particle physics. Whether the strange radio signals from Antarctica ultimately represent new physics or subtle systematic ECTs, they have already contributed to the evolution of scientific method and philosophy. They demonstrate how science progresses through the creative tension between conservation and revolution, between skepticism and openness, between individual insight and collective judgment. The Anita anomaly thus stands as both a scientific puzzle and a philosophical mirror, reflecting fundamental questions about how we acquire knowledge about the natural world and how human communities navigate the uncertain boundary between the known and the unknown. 10 years have passed since the first anomalous signals emerged from the data of a balloon floating high above the Antarctic ice. A decade of analysis, debate, theoretical speculation, and technological innovation. A decade in which the impossible has refused to become possible, and the impossible has refused to disappear. The strange radio signals from Antarctica remain unsolved, suspended in that peculiar scientific limbo between mystery and discovery, between artifact and revolution. They persist in the data like stubborn ghosts, defying explanation, yet demanding attention, challenging our understanding while eluding our comprehension. Perhaps they will one day be explained by mundane physics, a subtle error in calibration, an overlooked atmospheric effect, a complex interplay of ice and radio waves that creates illusions of impossible particles. The history of science is littered with anomalies that seemed revolutionary until conventional explanations were finally discovered. Cold fusion, polywater, faster-than-light neutrinos, each promised to overturn fundamental physics before revealing themselves as experimental artifacts or measurement errors. Yet the Anita anomaly has shown remarkable persistence. Each attempt to dismiss it through conventional physics has failed. Each search for systematic effects has come up empty. The signals remain genuinely anomalous, unexplained by known physics and unconfirmed by independent experiments, yet undeniably present in the data. If future experiments like PUEO confirm that these signals represent genuine new physics, the implications will ripple through every branch of science. Sterile neutrinos would revolutionize particle physics and cosmology, potentially explaining dark matter and solving fundamental puzzles about the universe's structure. Supersymmetric particles would vindicate decades of theoretical work and pen pathways to unifying all fundamental forces. Evidence of extra dimensions would confirm string theory's most basic predictions and transform our understanding of space itself. And if the most exotic interpretations prove correct, if the signals represent evidence of parallel universes or interdimensional interactions, they would force us to reconceptualize reality itself. Our universe would be revealed not as an isolated system, but as one member of a vast multiverse where different realities occasionally intersect in ways we're only beginning to detect. But perhaps the true significance of the Anita anomaly lies not in what it might ultimately reveal about exotic physics, but in what it has already revealed about the process of scientific discovery itself. The story demonstrates how science operates at its best, with rigorous skepticism toward extraordinary claims, international collaboration in pursuit of truth, and patient persistence in the face of mystery. The investigation has shown how modern science balances conservatism and innovation, maintaining healthy skepticism while remaining open to revolutionary possibilities. It has demonstrated the power of technological innovation to address fundamental questions, as improved detectors and analysis techniques push the boundaries of what can be observed and understood. Most importantly, the Anita story has revealed the profound human dimension of scientific discovery. Behind the equations and experimental data are real people, physicists, engineers, students, and technicians, whose curiosity and dedication drive the quest to understand reality's deepest mysteries. Their willingness to spend careers pursuing questions without guaranteed answers embodies the best of human intellectual courage. Whether the strange radio signals represent sterile neutrinos or systematic errors, parallel universes or atmospheric anomalies, they have already served a crucial purpose. They have reminded us that the universe is under no obligation to conform to human expectations. They have shown that even our most successful theories may be incomplete. They have demonstrated that reality might be far stranger and more wonderful than our current knowledge can encompass. The signals have also reminded us that Antarctica, that frozen continent at the bottom of the world, continues to hold secrets. Throughout history, Antarctica has been a place of mystery and discovery. From the heroic age of polar exploration to modern revelations about climate change and cosmic phenomena, the Anita anomaly continues this tradition, positioning Antarctica as a natural laboratory where the boundaries of known physics are tested. As PUEO prepares for its journey to the ice, as new detectors come online around the world, and as theoretical physicists continue exploring ever more exotic explanations, the mystery persists. The strange radio signals continue their silent testimony from the depths of Antarctic ice, waiting for human ingenuity to finally decode their message. Perhaps that message will prove mundane, a lesson about the subtleties of radio propagation or the complexities of particle detection in extreme environments. Or perhaps it will prove revolutionary, evidence of new particles, hidden dimensions, or parallel realities that transform our understanding of existence itself. Either outcome would be valuable. Science advances both through the confirmation of the expected and the discovery of the unexpected. The Anita anomaly has already advanced science by forcing physicists to question fundamental assumptions, develop new technologies, and explore theoretical territories previously considered too speculative for serious investigation. But until that final resolution arrives, the signals remain what they have always been: a reminder that the universe is stranger than we can imagine, more complex than our theories describe, and more mysterious than our instruments can fathom. They stand as monuments to the limits of human knowledge and as beacons pointing toward territories of understanding we have yet to explore. The strange radio signals that came from Antarctica may yet rewrite the laws of physics, or they may join the long list of scientific mysteries that ultimately yielded to conventional explanation. But regardless of their final resolution, they have already achieved something remarkable. They have shown us that even in an age of sophisticated science and advanced technology, the universe can still surprise us, still challenge us, and still remind us that the deepest questions about reality remain unanswered. In the end, perhaps that is their greatest gift. Not the promise of revolutionary discovery, but the assurance that mystery endures, that wonder persists, and that the universe still has secrets left to reveal. The strange radio signals from Antarctica whisper a truth as old as human curiosity itself. We have not yet finished asking questions, and reality has not yet finished providing answers. The story continues, written in radio waves against the infinite silence of Antarctic ice, waiting for the next chapter to unfold.